Hi, y'all. My name is Robert. I'm on the Relay team at Facebook, which is part of the React org. You can follow me at @statisticsftw on Twitter, and you can check out the Relay project at relay.dev. So today I'm going to talk about why Relay needs a GraphQL, why Relay needs a compiler, which is written in Rust, and also why we rewrote the compiler, which was previously written in JavaScript, in Rust. But bear with me here. I haven't given this presentation in a few months, so I apologize if it's a little bit rusty. Hey. All right, now you know exactly what to expect here, and also you know what my fiance has been putting up with. So, so real quick, what is Relay? Just a survey. Who here knows what Relay is? 3 people. Okay, excluding my coworker. That's great. Okay, so Relay is a framework for building and managing, or for building applications that use GraphQL data. In particular, building React and React Native applications. So who here is familiar with what GraphQL is? Much larger set of folks. That's great. Okay. So question is, why do you need a framework for fetching and managing GraphQL data? Why can't you just make an API call? Like, that's how we've been doing it in the past. It worked a year ago, worked 2 years ago, worked 5 years ago. What has changed? Well, let's start with this example here. Don't worry about the details. Just know that it's a bunch of React components that are nested. And in this hypothetical example, each component fetches its own data. So how does this component on the right side actually present itself to the user? So first, the profile container will render. We'll have some sort of loading state for the profile container. Then each of the subcomponents will start to render. And as their network responses come back in some random order, it'll start to show up. And finally, this sort of like Instagram button shows up even later. It's a pretty simple example, but I think we can agree that that's a lot of loading states to show to the user. It's a little bit chaotic, and it's certainly not the best developer experience. But there's other reasons that it's not ideal. So first, it's slow. The nested components didn't start their network request until the parent component had loaded. So in particular, that Instagram component, it was like third in line. And that's not a great loading experience. That's not a great user experience. Secondly, there's no deduplication. If one of those components fetched the name field, and another one did, it would be fetched twice. That's costly on your servers. It's not ideal. If the name happened to change in between those 2 requests, it might not, it might be inconsistent. Not ideal. And lastly, the loading states that we showed the user, they're ad hoc. They're based on how we divided this component into subcomponents, not based on what we think is best for the user. Okay. Maybe we don't need a framework. Maybe we just need to fetch all the data at once. So let's explore that. So if we have one big query, we just at the parent, we describe all the fields that we want, we make that API call, and then we pass it down to the children. So this would look like this. One loading state, it finishes, it all renders. That's actually a pretty good user experience, and it's really not bad. But now imagine you built this page, you're really proud of it, and you come back, and now a couple months later, your PM comes to you and is like, hey, I don't want that Instagram button anymore. So you go to the query declaration and you say, OK, I'm going to remove this Instagram URL field or whatever. But can you do that? Are you sure? Because maybe another component in the meantime has started to use that field. Now you have to sort of look at all the components. Also, what if somebody is landing a new component that starts to use that Instagram field at the same time? And just lastly, what if one of these other components is implicitly depending on the Instagram field, for example, via like JSON.stringify of the network response or an object.keys call or something like that? So the safe thing to do is to only ever add fields to the parent query. So your app over time becomes bloated, it becomes hard to know what you can remove, and basically you can't move fast. So the problem here is that there's an implicit dependency between the query declaration, which is in one place, and all these subcomponents, which are in other files. OK, so let's compare these 2 ways of doing this. One query, better performance, it's all one network request. There's deduplication sort of built in, one loading state. It's kind of nice. On the other hand, if every component fetches its own data, it's easy to reason about the components in isolation. It's easy to remove fields. It's easy to move fast. And, let's think about it. Let's unpack that for a bit. It's not that every component has to fetch its own data. It's actually that every component has to declare its own data. So that's what Relay gives you. Relay allows you to declare the data that you need at each subcomponent, but then there's a compiler step that gathers all these fragments, GraphQL fragments, and compiles them into a single query that's executed for the entire page. So you get the best of both worlds. You get one query with better performance. You get to choose your loading states, and yet you don't have to worry about removing fields when they're no longer used. So let's take a look at an example. Don't worry about the details here. These are just two components, each of which declare some data that they happen to use. And what the Relay compiler will do is it'll scan your JavaScript files, find these fragments, and turn them into a single query. So this is some sort of query that's been compiled for these guys. And one thing that you'll notice is that the name field shows up in both the top and the bottom fragment. And yet it only shows up one time in the final query. That's great. It means better performance, there's deduplication, and also, if you no longer need the name field in one of these components, you can remove it, and if it's selected by any other component, it will still show up. It's safe. So that's why Relay is great for applications where multiple developers are touching a bunch of components at the same time. It allows you to sort of move quickly without coordination because the compiler does all the work for you to build like sort of the optimal query that you could have possibly built. All right, so, but that doesn't really answer all the objections. What if one of these components is accessing the other data that it didn't declare, or it's accessing it accidentally via some sort of JSON.stringify or something like that? Well, we're not actually passing the network response down to these components. Instead, for each of these fragments, Relay will actually just read out the fields that they specifically requested. So this top guy here gets the name, profile photo, and URL, but it doesn't get the bio or the Instagram or the URL at runtime in practice. So that means that there's no possible way for these two components to interact based on the addition or removal of a field from another one. All right. So that allows all these components to be reasoned about in isolation. And in particular, what this means is that you can reason locally, but the Relay compiler will help you optimize globally. All right, so that's the spiel about Relay, and now we're going to get to the Rust part, which is the more interesting part and why y'all are here. So let's talk about why Relay needs a compiler. So first, it needs to scan all of your JavaScript files to find these fragments. The JavaScript might not have loaded at the time. So for example, you might have a page that's only visible, that's lazy loaded, like the JavaScript is lazy loaded. We nonetheless want to know about that fragment because when we make the API call earlier, we want to fetch that data. So of course we need to scan things in advance. Secondly, the Relay compiler does a lot of work at compile time to optimize your query. For example, if there are parts of your query which are unreachable, given like given some static parameters that you pass to it, it will prune those. And it will do a lot of other work. For example, basically creating a data structure that makes it very efficient to write the data that you got back from the network into the Relay store and to read back out from the Relay store the data that is currently stored there. So all of this work doesn't have to happen at runtime. And therefore, you get better performance. OK. So why rewrite the JavaScript compiler? So the obvious answer is that JavaScript is a bad language for compilers. However, that is not sufficient to convince the bosses. So instead, it's actually that performance was slowly degrading. So at Facebook, we had an increasing number of queries and fragments, and the performance of the Relay compiler just couldn't keep up. We tried a whole bunch of sort of micro optimizations, but they just weren't going to get there. We needed something bigger. So why did we choose Rust? And of course, the obvious answer is that of course you should choose Rust. It's a great language, and that's it. But in fact, we considered a bunch of other languages, such as C++, OCaml, Java. They chose Rust before I joined, so this is, I'm not exactly sure how this all went down. But the point is, we considered a bunch of languages. We wanted safety, support for multi-threadedness, a lack of footguns, and great runtime performance. And pretty much only Rust checks all of those boxes. Now, the big wins that we got from Rust aren't anything like super fancy. In particular, it was just that we could easily share large immutable data structures across threads. So in particular, the schema representation can be multiple gigabytes of in memory. And if we wanted to parallelize the JavaScript compiler, that schema would have to be loaded once per process. And that would quickly get out of hand. So we had a very hard limit on how much parallelism we could even theoretically achieve with the JavaScript compiler. Rust allows us to safely parallelize all that. And it's fairly easy. And also, it's got really good developer ergonomics. I'll talk more about that later, but that's the gist of why we ended up choosing Rust. I want to stop here. Any questions? Anyone want to? Cool. All right. So was it a win? Yes. Right out the box, performance improved 5x on average and 7x at P99. And some builds went from 5 minutes at P99 to about 30 seconds. That's, of course, because Rust has a much more predictable memory usage. There's no garbage collection pauses, all this kind of stuff. And this is comparing the highly optimized JavaScript compiler to the Rust compiler that shipped right out of the box. Presumably now it's gotten better, but that's the comparison that we have right there. And it was also just much easier to ship new features because the compiler sort of catches more of your mistakes. All right. So let's talk about the different compiler modes that the Relay compiler has. There are 3. There's batch mode, which just scans all your files, compiles them, generates the artifacts, and is done. There is watch mode, which does the same thing, but it watches the file system, and as the file system changes, it will recompile just the parts of just the queries that need to be recompiled. And the LSP, so the VS Code integration. This powers things like if you hover over a fragment, it'll tell you, hey, this is a fragment on user. Or if you hover over a field, this is a field on user, and here's its description, and maybe it's deprecated. I'll go into more detail in each of these. So batch mode is the sort of most interesting one. I mean, not really, but it's the main one. So we'll talk most about that. So the batch compiler, it just does what you would think it did. It finds all the GraphQL schema files and files containing GraphQL literals. It parses the GraphQL ASTs. It builds and validates the schema. So the schema being sort of the description of all the valid types and all the fields that are available on each type. It collects these ASTs into what we call a program and validates and transforms the program. Again, I'm going to go into more detail into this. I'm just doing a whirlwind tour here. And then it writes all the generated artifacts. So those are the JSON structures that are used to read and write data from the network. And deletes the no longer generated artifacts. And it persists queries. Again, I'll go into more detail. So really the important ones are the validate and transform the program. That's sort of the meat and potatoes of what we do. And most of the time, if I'm shipping a new Relay feature, it's mostly in that section. Everything else is pretty cheap and more or less done. In particular, parsing the GraphQL ASTs is super cheap. We don't care if we do it a bunch of times. Building and validating the schema, fairly cheap at first. Actually, those results that you saw earlier involved us reparsing and revalidating the schema sort of on every change, and we only realized that later, but it's not that big of a deal to do it multiple times because it's not that big of a step. But we, of course, got rid of that once we noticed it. OK, so let's talk about transforms. So the program is just our data structure that represents all the queries that we are going to generate. So basically what we're doing is we're taking the program, we're calling some function that transforms it, and we're passing in a reference to the previous program. So for example, anytime you select an object, if it has an ID field, we'll also automatically select that ID field. Everything in the Relay store is keyed by ID, so it automatically results in sort of data consistency. We generate refetch queries. You might have a situation where you're looking at a particular user's profile and you have a drop-down to change the user that you're looking at. It will just refetch that section, that subsection of a query and replace it with new data. That's really nice because auto-generating that means that you don't have to ever worry about forgetting to select a field in the refetch query or selecting more fields than you need or anything like that. It's just all done for you. We also ensure that no fields conflict. So if you're familiar with GraphQL, you'll know that you can't select a node with ID 4 and right next to it select a node with ID 5. Because in the actual network response, those will both come down under the node key. So this transform needs to make sure that at no point in time in the queries that we're generating do we have like conflicting selections. And that's in red because that's actually the majority, I mean, not the majority, I don't really know if it's above 50%, but that's the largest, most expensive transform. And pretty much everything else is dwarfed by the fact that this transform needs to have global knowledge of all the fragments you select in various places, and it therefore just runs the slowest. Okay, so another thing you might have noticed is that we get a program and we pass in a reference to the previous program. So somewhere in here, what we're doing is cloning. And that's bad. We shouldn't do that, obviously. But the thing is, the program is actually wrapped in an arc, so an atomic reference counted pointer. And it's really cheap to clone it. We only recreate the program if we're modifying it. And most of the transforms don't really do, well, the happy path doesn't modify the program in a lot of cases. And so I would have thought that this would be expensive and something we should worry about. But given the fact that the previously mentioned transform that checks that there are no conflicts is such a disproportionate share of the compile time, this actually just doesn't matter. And so moral of the story is benchmark, find out like what matters, because most people don't have a good sense of what will matter in the end. And a lot of times just like arcing all the things, it's fine. It's fine. It doesn't really matter. Okay. Let's talk a little bit about artifact generation. So when you compile a query, the artifact that's generated is two things. Artifact meaning just like the file that we generate. One is there's a flow type or a TypeScript type of the data that we read out and the variables that it accepts. So for example, if you have some query with a user and a name, it will generate some sort of object with a user field and a name field. And that's the result of what you would get if you read this from the store. And secondly, we also generate the runtime artifact, which is just this JSON, just this JSON structure that says, hey, this network response is going to come back. You're going to have a user field. The user field is going to have an ID and a name field on it, and here's what you do with it. And so there's really no runtime lookups. There's no checking like, hey, is this an object? Is this an array? Like, is this a scalar? We can basically, since we know exactly what the shape of the data is that we're getting back from the backend, we can encode that in a JSON structure, and then we can normalize, meaning we can write the data to the store a lot faster as a result. Last thing I'll talk about real quickly on the bash side is persisting queries. So persisting a query simply means that instead of sending the full query text with every network request, we actually at build time send that query text to the backend. The backend will then register the query and it'll send us back an ID. And then at runtime, we simply send the query ID and variables instead of the full query text. So this has several advantages. First, the server can pre-process the query text. So I'm not really that familiar with our backend, but presumably it does a bunch of work that it wouldn't otherwise have to do at runtime or at request time. Secondly, we save on bandwidth, both that the initial JavaScript doesn't have to include the query text, which can be very, very large, and also because the actual network request that you're sending out doesn't need to include the full query text. It just includes the ID. So this is a lot more efficient. But there's sort of a more subtle benefit to using this. and that's security. Because we don't accept raw GraphQL by our backend, only query IDs, we actually strictly limit the amount that an attacker can sort of explore our API. And on top of that, like if you try to send a network request for query 1 and you don't guess the correct variables, it's gonna just give you sort of a very opaque error message saying like, hey, this is just wrong. Just I'm not going to tell you why it's wrong, but like it makes it much more difficult for attackers to be able to explore our backend or explore the API and maybe get at something that they really shouldn't be getting at. So that's the gist of the batch compiler. Basically, it finds all the files, generates artifacts, and it tells the server about the queries that we're generating. OK, so let's talk really quickly about watch mode. So watch mode is essentially when a file has a change, we'll try to reuse as much work as possible and recompile only what's necessary. In the Relay compiler, the reuse is somewhat coarse-grained. Like we're not very precise about just recompiling the field that changed or something like that. We usually have to recompile the entire query to check things like that global checks that no fields conflict. I think if we were rewriting this from scratch, we would have been able to make this much more fine-grained and make watch mode performant. And also, watch mode has a nice feature, which is that if a file changes while we're doing some processing and additional file changes, we have like a bunch of checks to exit early if new changes are detected. And this is just some sort of atomic counter that like if it's gone up, we bail. That's it. OK, so the LSP. This is the language server protocol, which came out of Microsoft. And it's basically how a VS Code extension talks to the Relay compiler. And a lot of other extensions implement the same protocol. And it's actually really, really fantastic. Things that could be improved, but like it's really good. So the VS Code extension is powered by this. And basically, it's a request and response protocol that just answers questions like, hey, this fragment, where is its definition? Or this fragment spread, where is its definition? I'm hovering over something. What should I show? And what it doesn't do is it doesn't generate artifacts or persist queries, and it doesn't run all the validations so that it can be more performant. I think in the OSS version, we do also open up a Relay compiler in a separate terminal window when you run the VS Code extension. So you do get the artifact generation and the query validation, or the full validation. But what's actually kind of nice about the language server protocol is that you can extend it with, oh, sorry, that's the next page. So the architecture of the VS Code extension is that there's an event loop that listens to events, such as, hey, I want to go to this definition, or some file changed. They're processed and responses are sent back. So it's just like a server. It's just a server that responds to requests. The big question with the language server protocol, or with LSPs, is do we do the work in advance or simply at request time? So it would be ideal if when you hovered over a field, like the name field, only then did we realize that that name was on the user, which was on this or that, and like only did the absolute minimum work to figure out, hey, this is what we need to show the user at the time. It would be more performant, be less wasted cycles, all this kind of stuff. It's not exactly possible with Relay, because if you make a change, we want to show you all of the errors. So there's a good amount of work that we still have to do. However, it's really difficult for us because we started with a batch mode compiler to sort of rework that compiler and make it much more incremental. If we were redoing this from scratch, I would highly recommend sort of starting with the LSP architecture from day one, so that we could just recompile just the very minimal things and recheck the very minimal things in order to make the LSP more performant and just sort of less hacky, realistically. One thing that's nice that I sort of alluded to earlier is that there are custom LSP events. In particular, we added support for a graphical-like interface directly into VS Code, the Schema Explorer. So you can hover over a field. It says like this is on a user, and that user field or that user is clickable. You click it, and it opens up some sort of new web page essentially inside of VS Code that just shows you, hey, I mean, in this case, we're looking at the node interface, and it shows the description, it shows the fields that are on it, and it shows what objects implement that interface, stuff like that. There's nothing really fancy about this. It's just a website. But what's nice is that it's powered by the LSP. So the VS Code extension sends a specific message, and then the server, which is basically the compiler, responds with like, hey, I understand that message. Let me send you some arbitrary JSON back. And that's really nice because you too can have an LSP that does something more than just like hover and go to definition. All right, so we'll conclude a little bit with some things that went well and some things that could have gone better with the compiler. So first, Rust is actually a really good language. It was really easy for a bunch of JavaScript developers to pick up. I think in particular, the learning curve is not as bad, especially if you're working in an existing project where you're just adding features incrementally. Maybe starting a new project off the bat can be a little bit intimidating, but it didn't end up being that hard for a bunch of JavaScript developers to do this. Great time to take a photo. Really selling Rust here. All right, secondly, Rust is fast. And in particular, like the straightforward solution and the easy solution can often be good enough. Like I mentioned earlier, everything is wrapped in an arc, so we don't really worry about cloning inside of the transforms because like so much of the work is done within a particular transform where we're not doing unnecessary cloning. And focus on what matters. Like it's really important not to focus on micro-optimization and instead get a sense of where your effort really makes a difference. And in particular, how you find out where it makes a difference is with benchmarking. We have a good set of dashboards internally so we can see when a change, or when the performance of a particular transform has started slowing down, and we can really estimate and we can figure out like, hey, was that associated with some sort of change? And this helps us figure out like whether we expected the performance to degrade or whether it's unexpected and we should investigate. Okay. Next, you should intern strings. So strings are somewhat expensive, heavy weight data structures, and the Relay compiler uses and manipulates a lot of strings. And instead, one thing we found that works really, really well is we intern them. So basically, whenever a string is encountered, we look up in a vector, like does it exist there? Presumably, there's like a hash map of the indices. If it's not there, we add it to the vector, and we replace that string everywhere it's used with just an index into that vector. So now, everywhere we manipulate strings, everywhere we pass around strings, we're actually just passing around a single index, which is much cheaper, much lower memory use, and it works really well because we never really need to mutate strings. If you need to mutate a string, you sort of create a new one and then re-intern it. And that's like such a small % of the time that this ends up working quite well. Actually, one thing. Also wrap them in new types. So stringly typed things are bad. It makes it really easy to make mistakes. And what Rust allows you to do is to have like sort of zero cost wrappers around these types. So in particular, in our compiler, if you're using an operation name, you can't pass it somewhere that's expecting a fragment name. You can't pass it somewhere that's expecting a directive name. It's a little bit annoying to do, but you prevent a single bug in this way, and it makes it all worthwhile. But it's quite nice, especially if you reason about this from day one. Retrofitting this onto an existing code base, more annoying than starting off with everything being wrapped in a new type. You should abstract the file system and parallelism. In particular, we have two sort of demos on relay.dev of the compiler running compiled to WebAssembly and running inside the browser. One's like a sort of an AST explorer, and one is a code sandbox where you can manipulate some Relay or actually like use Relay without installing it. Obviously, the file system doesn't exist in WebAssembly, and neither does parallelism. So abstract those away and have some sort of compile time flag that checks, hey, am I compiling for WASM32? If so, par iter is just like a regular serial or synchronous iterator. Start with the LSP in mind. I alluded to this earlier, but there's basically, you can either have a push-based architecture or a pull-based architecture. And it's fairly easy to go from a pull-based architecture to a push-based architecture, which is to say, a batch compilation of an incremental compiler is just like asking, like, hey, I want to recompile everything, and it just works. But if you're going from a batch-based compiler that only knows how to compile everything, and we're asking, hey, just recompile this one tiny step, like, it's not obvious how to answer that question. In particular, Rust Analyzer, Matt Kladd or Alexei Kladov, and the Rust Analyzer team have a bunch of really, really amazing videos on YouTube that go into a lot of detail on this. And that's like sort of my Bible when it comes to figuring out how to architect this correctly. Also, Salsa is the library that they use, and there's a lot of really good videos related to Salsa. So next thing I'd say is focus on compile time. There's like a number of tricks that you can, there's a number of things you can avoid that the Relay compiler does not avoid, such as don't have central crates where that everything goes through. So you imagine like in a front-end project, you might have like components and utils and stuff like that. And like components reaches into utils a million times, and utils reaches into this or that a million times. Instead, it should be sort of vertical. That way, like if you're working on a particular feature, only sort of that like vertical slice needs to recompile. The reason for this is that the compilation speed, most of the time what you'll be doing is implementing a new feature. The compiler will tell you you're wrong. You'll go fix what it says is wrong, and then you'll go back to this. So like the iteration speed is really a critically important aspect of how fast you can ship features. Shipping features quickly is good. So I would also, in particular for compilers, this is very easy to not worry about this, but like worry about N/M problems. So in Relay, we have a lot of advanced-ish features like the required directive. We have resolvers. We have refetchable queries. And they're easy to test in isolation, but it's really, really hard for us to know, like, do all of these features work well together? And the answer is most of the time, probably not. Like, there's probably cases where we have bugs. And the reason that this is really easy for us to introduce bugs in this way is because our representation of the abstract syntax tree and our internal representation, or our intermediate representation, like, they're too low level for what we're trying to do. So I would in particular advocate for having many IRs. One example is resolvers. So resolvers are a term that we use for there's a function that's accessible through the graph. It goes from some source data, and like you access the result of that function. So it might select first name and last name and locale, and it gives you the full name along with some sort of contextual information. It's really nice to be able to select a full name field and not worry about, not do all of that work yourself as an application developer. Internally in the AST, we have no way to represent that. So what we end up doing is we have an inline fragment with a special directive. The first selection is the resolver field, and the second selection is another inline fragment containing the data that the function depends on. So like that's super fragile, and that's really easy to accidentally screw up. And in particular, you sort of, if another transform is working on that data, on those selections, it might do the wrong thing, and it might collapse them. It might, realize that it's not accessible and like prune some fields, but like that might not be the case. That might not actually be correct. It would have been much better if we were able to represent resolvers, require, defer, all this kind of stuff in a more native and sort of like in a way that really matched the needs of the transforms. Another aspect of this is, sort of make impossible states unrepresentable. Inside of the Relay compiler, we have this enum. Don't even worry about reading it. But the point is, it's got six variants. There are input objects on there, and there are objects and interfaces and unions on there. And at no point in time is there ever a point in which a variable can be either an input object or an object or interface or union, according to the GraphQL spec. So that means that we have all of these sort of awkward situations like this. Again, apologize you can't read it back there. But basically, we're panicking if we encounter the wrong variant of the enum. Like whenever that happens, that's really a smell. And it just makes you less confident in the correctness of the compiler. In practice, it isn't so bad because we have such a large code base. So I would also really strongly advocate for using functional programming to prevent bugs. We have a lot of transforms which use a sort of a pattern where you take a mutable reference to self, you modify that self object at some point in time, and then later you access it. And there have been a number of bugs where we modify the self object, then we use it for something like artifact generation, and then later we call other functions on that self, which also mutate it. And therefore we miss things like there might be imports that we should have learned about in order to add to the generated JavaScript file that we don't add because we didn't use regular functional programming techniques to make that impossible. I would really, really strongly lean into that. It's actually really, really nice to be able to say like, hey, this looks like a bug because we're creating a new object here, but like we've already previously consumed the object. And the Rust compiler like makes that very easy and does a lot of that checking for you. But we don't have like that many bugs, I think, because we actually run this against an extremely large corpus. So in particular, we have some absurd number of queries and fragments. And every single time we ship a change, if any of those generated artifacts is different, that change won't land unless you manually sort of rerun the compiler in the new state and like sort of say like, hey, yeah, this is actually what I wanted to do. If you don't have a large code base like, and when we were rewriting the JavaScript compiler to the Rust compiler, that was really useful because we just had a dashboard that said, hey, as of currently, like 1,000 files have been generated differently. And we just saw that number go down. And when it got to 0, it wasn't the be-all, end-all because there were things that the new compiler might accept that the previous compiler would have disallowed, or cases that hadn't shown up in the code base that were being incorrectly handled. But we were fairly confident that we got to parity or very close to parity. And if you don't have this extremely large fixture, invest in fixture. If you don't have a large corpus, invest in a lot of fixtures. Also drink water, so you can speak. These won't catch a lot of the bugs. In particular, like, we've had just issues where you might have to like recurse like 2 levels deep before you encounter a bug, and our fixtures are all 1 level deep because who writes anything deeper than that? Like, come on. Maybe like ChatGPT or Copilot will suggest like maybe you need it too, but we're not like that. We're not. But fixtures nonetheless help. They catch like a good amount of bugs. But make sure they're actually testing the right things. It's really easy for us to write fixtures and then just notice later on that like entire code paths are just not affected by fixtures. Last thing, I promised the last thing. Encode white space and comments in your ASTs. In particular, you can't make programmatic changes and quick fixes if you don't encode white space and comments in your ASTs. We didn't, and we still haven't, which is sort of annoying because if you're building a compiler, the interface that you're providing to your users are the errors it shows, the hover information and other sort of VS Code integration type things, and quick fixes. And if you don't have one of those 3, like you're hobbling yourself. So encode whitespace and code comments so that you can take it, manipulate it, and spit it back out with the minimal number of changes, and your users aren't mad that like everything gets reformatted. Or do something like prettier and just like force them to be in the same format every single time. That also works. In that case, you only really need to encode comments if they're allowed. Yeah, that's the Relay compiler in a nutshell. Happy to answer any questions. Happy to Yeah.
I have a question.
Yeah.
This is probably all boring stuff to you, but it's my life right now. So I'm wondering, like, what kind of infrastructure did you use to implement the LSP? My understanding is it uses JSON RPC. Is that correct?
There's a crate that provides most of the LSP types
Gotcha.
that we use, and it does all the deserialization and serialization. So we didn't actually have to. I mean, other than that, which did that aspect of it, it's just an event loop that listens to events from a number of streams and responds to them. But I think we more or less maybe copied, roughly copied the Rust analyzer style event loop.
Mm-hmm.
But it didn't really require like that much like heavy infrastructure, if that makes any sense. So.
Gotcha.
You mentioned Salsa. Are you using Salsa?
We're not using Salsa,
Okay.
but I want to. We're inspired by it, so yeah. Although on the runtime side, there is a project to rewrite the store to make it more, the store being the data structure that keeps track of data at runtime in a Relay app, to make that more incremental. And that's also influenced by Salsa, but again, doesn't actually use the library. So.
Yeah, I think that's a very good point that you made about structuring your compiler to answer essentially point queries.
Mm-hmm.
I think there was like a large refactor of Rust C actually along these lines.
Oh,
like
interesting.
in the
I didn't know
past.
this.
Yeah.
Okay.
And
Yeah.
I'm pretty impressed that they managed to pull that off.
Yeah. There's a lot of smart people working on the Rust compiler, so yeah. I'm glad they can pull it off. What hope is there for the rest of us?
Worry about any compiler transcription between JavaScript and Rust during this transition, or only LSP solve all the problems?
So the LSP was added after the fact. So when we made the transition from the JavaScript compiler to the Rust compiler, we had a dashboard that kept track of whether there were any differences. And when it reached 0, we were fairly confident that we had reached parity. Other than the fact that we also added some specific tests to make sure that, like, hey, if this is rejected by the JavaScript compiler, it should also be rejected by the Rust compiler. I don't really remember if we just wrote tests to assert that, or if we found situations where found commits where the compiler failed to compile on the JavaScript side and made sure that it also did the same thing with the Rust side.
And are you guys using like ECMA, not definition, like ECMA specs, like the latest ECMA specs for these, or?
So there's a GraphQL spec and that's mostly what we try to implement.
So you rely on GraphQL instead of?
Yeah, I mean, we're not parsing any JavaScript.
Okay.
So when we read your JavaScript files, we literally look for the string GraphQL and then a backtick, followed by something and then a backtick. And if you import the right GraphQL, it works. If you just have some other function called GraphQL, we'll still try to compile it and it won't work. But that's okay.
Sorry.
It's all good. Yeah. I got the answer right. You know, what's my prize? Yeah, GraphQL is the secret word. Yeah.
Did you first think about replacing each JavaScript line to Rust, or you already knew that you need to think from scratch to build something from scratch?
We more or less replaced it, not exactly line by line, but we did a lot of like line by line replacement. We didn't try to like integrate like to shell out to JavaScript or to Rust or anything, and then go back to JavaScript. None of that. But like some of the more, shall we say, complicated or spaghetti code like code had to be rewritten sort of line by line in order to, because we couldn't reason about it otherwise. And so a lot of the code like isn't very idiomatic in Rust, and it's going to take some other passes to really clean it all up.
So the performance improvement is majorly coming from the translation from Rust to JavaScript, and it's not really coming from the code organizational changes.
Yes, yes.
I see.
Because we were able to do basically two things. One is share the schema data structure across threads, and also parallelize a lot of the validations and transforms, which all reference the same schema and other immutable programs. But basically, we were able to easily parallelize things. And there maybe is also some benefit to Rust being overall faster than JavaScript, but like probably not a huge. That's probably like less than the. That's less important than the parallelization aspect of it. So obviously there was no parallelism in the JavaScript compiler, but like that's the big architectural change. Otherwise, it's roughly same-ish. So.
So what tools slash frameworks do you use to measure the performance? So remember you said when you switch to a new compiler, it quit five times more. So
Yeah.
what tools do you use?
So internally, we have basically we emit events at a bunch of points in time in the compiler. So let's say we're starting the transform pipeline, we're ending the transform pipeline. And internally at Meta, we have really good tools for just sending those events into the cloud and then creating dashboards from those. It's like, hey, on average, the amount of time between these two events was blank, and on day one, the average time was 5 seconds. On day two, it's 4 seconds or something like that. So just a bunch of really great internal tools. And I have no idea how I would do it if not for that.
And there are not open source.
Yes, they are not.
Oh,
Yeah. So.
Regarding testing, you mentioned that it's important to test for n times n programs.
Yes.
Like you test one feature in unit test, but it doesn't work well with another feature. You also mentioned that it's useful to use fixture, but did you consider doing a combination n times m with your fixture, pair features, and you basically test all the possible combination? Did you consider this kind of thing, or you just tested on a very large context?
I don't think we have seriously considered making our fixtures have every single combination of them, of features. And I think the issue with that is that it's not immediately obvious what features.
Listing, right?
Yeah. What features and exactly how they need to interact to sort of be problematic. So I'm not sure what we would really do in that kind of a situation, how we would do that in that kind of a situation. It's kind of a tough problem. Sorry, did I answer your full question?
Yeah.
Okay.
I just wanted to
Yeah. No, I wish I had a better answer. If you have a better answer, I'm all ears because it's frustrating. Yeah.
I think we had a presentation a month ago about something similar.
Oh yeah. No. I think I saw a hand over here. Did I? Cool. Well.
I got a couple of questions for you.
Oh yeah,
actually,
absolutely.
if you don't mind.
Yeah,
So I'm
please.
wondering, how did you get into programming when you started?
I took some programming classes in high school, but I really became a professional programmer, I guess you could say, when I worked for a company and I did all my work in Excel. And I ended up just starting to automate more and more of my job away using the built-in VBA environment. I think that's mostly how I got started. And at some point in time between high school and when I was 23 or 24, Ruby on Rails became popular and all this kind of stuff. And I started learning programming. And I was like, wait a second, this is a lot easier and a lot more approachable than
Visual Basic.
run Java C and now you have a program. But how do you expose it to the outside world? I don't know. So it just became, I think, a little bit more accessible at that point in time.
What language did you use before getting into Rust?
Mostly JavaScript. think mostly JavaScript.
That sounds like a rough transition.
So it took me 2 tries to get really into Rust. The first time I like read about it, I was like, this is really cool, I want to learn it. And then I tried and I kind of more or less failed to like, you know, to make the jump. But then later I found the Rocket framework, the Rocket web development framework. And I thought that was just super awesome. And it like really helped me just like actually build up a project that was just a little bit more involved. And I feel like that's when I finally figured out what's going on. And then from then I just started, you know, just hacking around and building things. So
I think I heard this from the previous speaker who built a keyboard firmware in Rust, that
oh, nice.
he tried multiple times, and every time he tried, it was like less friction. So maybe the third time he actually got into it.
Yeah, yeah. Yeah, no, I think that's 100% the case. And then having something specific that you can build that's not just like, hey, you know, write a hello world or, you know, an iterative for loop or this or that. Like, maybe that works for some people, but having something like concrete to focus on was really helpful. So.
You seem to be really big on pure or like functional programming. Have you tried any functional languages?
Not more than just like a hello world thing. Yeah.
Which one was that?
I mean, I've tried Haskell. I've like, that's pretty much it. Like, I mean, I don't know. I haven't tried that many different languages. So I guess I have used a little bit of PHP due to where I work, and I'm sure a few other languages. So, yeah.
All right. I have one final question, which I usually ask presenters. If you could pick the topic for the next person, what would be that? What is something that's like really interesting to you that you want to learn about?
I think how the Rust compiler works internally. I have no idea, and I think that's like
That's
would
a
be a
tall
really
order.
fun. Just like some aspect of that would be really fun to learn about.
That's a good answer.
Yeah, no pressure, guys. So
All right.
yeah,
Thank you very much, Rob,
thank you.
for the presentation.